Now we will go forward with some of the applications. Before we begin, let's recap on one important thing to notice. We said that we are getting a uniaxial PML which is pretty generalized for all directions, as you can see in the slide. For most of the practical application, we will keep the thickness of the absorber as 1 lambda, which is roughly, as a rule of thumb, 15 layers of triangle sitting, and we are not worried about any direction like x or y. So we are able to get a generalized formulation that will enable us to model any particular thing. So if you wanted to do an antenna which is sitting here, this is perfect. So this is what we are going to see in the next slides as an application. To begin with, we will start with waveguide problem. So in the waveguide problem, we are using simple PML truncation, and the measurement points are here. The measurement points are basically points to evaluate what is the reflection. How we are doing that is something important to know. So what we are doing is, for the reference solution, we are making this a very large waveguide. So we are not seeing any reflections coming back, so it's a very large waveguide, and we are able to subtract the reflections coming from here from the very large waveguide to get the reflection field that is getting reflected. We are using a first order TE mode. The boundary conditions for the waveguide are PEC on either side. We are truncating the PML using also a PEC, and as we said, we have DABS, which is the thickness of the absorber. So this will, with this geometry, you can see this is how the wave truncation looks for a practical waveguide simulation. So this is the top view, and you can see the PML layer is starting from here, and you are able to see what is happening in the PML layer, and this is a side view. The operation is very much as expected. When you see, there is not much reflections from the PEC condition, because sometimes when you have PEC wrongly coded, you might see that the modes will not be going in this manner. You might have certain errors, spurious errors. These are numerical errors. So you will know when the boundary conditions are given properly, and you can see how the waveguide is being truncated using a simple PML case. What we are seeing here is the result of this truncation. Something particular about this, it's a graph that tells us quite a lot of information. These information are very important for any scientist or engineers who are using numerical methods, because this tells what is the computational cost aspect, how much trade-off we have to do, what are the reflections and things of that sort. So I'm going to explain, I'm going to take time to explain the meaning of this particular graph using the case of the truncation what we saw now. So what is happening here is, as you can see, there is on the x-axis, you see that the frequency is increasing. So when the frequency is increasing, the value of lambda is going to decrease. So let's discuss this using the slide here. So what we see is, when we have the frequency is increasing on one axis, so frequency is increasing. So we also see that the lambda value, so frequency is going to increase in this direction, and lambda value is going to decrease in this direction. So that means, let's say we have a lambda is equal to a particular length. When we are increasing the frequency, the lambda values are going to be lesser and lesser. So this is the value of lambda. So that means, for a particular increase, what is happening is the number of cells that are going to sit within this lambda. So let's take a simple example where we say, so this is lambda 1, this is lambda 2. Let's say that we are having, in the first case, 1, 2, 3. There are 4 cells for this lambda. But in the case of lambda equal to 2, there is only 1 cell, approximately for the same discretization. For this lambda, it will see. So in this case, there are 4 cells, and here there is only 1 cell. So from the discretization point of view, from the spatial discretization point of view, increasing the frequency is going to create a poor performance, because the lambdas are going to become smaller and smaller. Accordingly, the number of cells, so the number of triangles in the case of a 2D is number of cells per lambda is going to decrease. So you expect, as you increase the frequency, the performance should deteriorate. So that is one thing. But if you see in this slide again, when we are increasing the frequency, what we are computing here is a numerical reflection in decibel. So we are taking the 20 log natural logarithm and we are computing it in dB. What you are seeing here is, when you are increasing the frequency, the black line is the line for theory. So theoretically you should see how the reflection should decrease, and this is the performance of the Siller-Muller boundary condition, which is one of the state of the art before PML was used. This is the boundary condition that they use, and there are quite a lot of PMLs. So Béranger PML, Maxwellian PML and all these other types which we discussed before. What you are seeing here is, as we increase the frequency, the performance of the boundary condition, whether it is Béranger PML or whether it is uniaxial PML, whatever it is, the performance is improving. And also for the case of Siller-Muller boundary condition, the performance is improving, which is contrary to the case of what we thought, as the number of discretization is becoming coarser and coarser, there should be more numerical error, but something else is happening. What is that? So that is something that we need to know. So what is happening here is, when we are increasing the frequency, when you are talking about a mode is basically superposition of two waves that are going in opposite direction and meeting them. So let me explain here in the slide. So when you are talking about mode that is propagating in this direction, what is happening is, you are basically having so these are the two waves. You can think of them as plane waves going in this direction, and then they are going in this direction. This is the theta. So this is the angle of incidence. So when you are computing what is happening here, so this is the theta, this is the angle at which it is going to impinge the PML layer. So here is where the PML is sitting. So what we are talking about is, as we increase the frequency, we are coming closer and closer to normal incidence. So what we see is, when theta is becoming 90, so this we said that this is the value of the theta, and we said this is theta, and this is the direction in which we are feeding it, this is the direction in which we are truncating it. So when theta becomes closer and closer, when frequency is increasing, theta becomes closer and closer to plane wave. So what is happening here is, when frequency is increasing, this theta value is going to change. So theta is going to increase, and when frequency is very, very high, we are coming almost like a plane wave. So in this case, theta will be 90 and the direction will be a normal incidence. So this you can see also in the previous slide. When theta is increasing, the distance between the red and blue will become narrower and narrower. Let us say for now, so this is the distance between the blue and let us say this is red and this is blue. So what is happening is when theta is increasing, this one will be coming closer and closer. So this will be the definition of lambda, and this lambda is going to go smaller and smaller. So what you will see is when frequency is quite high, you will almost see them like a plane wave. They will be like a plane wave going and hitting the PML surface, and that is what is happening in the case of this example. When I am going to increase the frequency, what I will have is pretty much like a plane wave, and this is the reason why, although the lambda is decreasing and the spatial discretization is going to be poor. When I say poor, we are having less number of layers per lambda minimum. Still the PML and the Silver-Miller boundary condition is performing better, because we are coming towards the normal incidence as the frequency is increasing. The exact opposite is going to happen at lower frequencies. So when the frequency is becoming less and less, irrespective of the fact that there is going to be more number of cells per wavelength, we see a poor performance of the PML and also the Silver-Miller boundary condition. So we see that as we increase in lambda or as we decrease in frequency, the performance is deteriorating, and this is the importance and also the uniqueness of this particular graph. And as you can see, this is the propagating mode where we are talking about. There is some evanescent region which we are not very much interested. We are interested in the propagation region, and we see that this is very much going as per the expectation of the theoretical value. So with this we are able to see couple of important factors, and we will go into the next application. The factor number one is the PML is working fine as expected, and we are able to see what is the trade-off that as a scientist or as an engineer you have to do to make sure that your computational cost versus accuracy is maintained. With this we can also see that for any of the plane wave or waveguide truncation, a lambda minimum as the thickness of the PML and roughly 10 to 15 cells is quite good, and this is what we have seen also in the example we have shown here. So with this we will go into the next application, which is the radial application. I discussed the radial application in the previous module, where we say that the direction of anisotropy is in the radial direction, and we are going to see what is the impact of location of source or a scatterer. So assume that this point is a source. It can very well be a scatterer where you have plane waves coming in one direction, and you are kind of truncating in the manner which is shown. So again, so this particular point can be a source, or so let us say you have plane wave coming. So the position of the source or the scatterer is going to be very critical, because it is going to change the way in which the radial PML is going to see incoming waves. So ideally you want them to be normal in all direction, which is not possible for most of the application, because we can't keep always a source at the middle, or we can't predict the way in which the wave is coming. But we try to make sure that we are able to have a good compromise in terms of the radius of curvature. So this is the radius of curvature. We are making the radius of curvature as small as possible for the case of numerical computation, and as large as possible so that we can reduce the number of numerical error or the value of the numerical error. So with this we will see here, when I keep the source exactly at the center, as you can see in the slides, what is going to happen. So when the source is exactly at the center, all the points are going to be more or less in the normal incidence. So it should be the best case scenario where we will see we are having a PML, radial PML sitting here, and we are truncating using a PEC. So the red line is a PEC and the source is, let us say, a kind of a sine modulated Gaussian pulse. What you see here is the pulse is going and you see that some amount of reflection is coming and then it is focusing exactly at the center, and this is as expected because this is like a radial mirror which is putting all the reflected fields exactly at the center. And let us see if I can change this source position elsewhere. So instead of putting it at the center, I am making it go on the point as it is shown here. So for most of the points which are exactly at the opposite, it will be still normal incidence, but you will see on this point and this point it is no longer normal incident, it is kind of a grazing incidence. So accordingly we will see the performance of the PML will be slightly worse than the initial case, but still good enough for most of the practical application, and you will see the focusing effect has moved from the center as expected to the exact mirror point which is on the other side. So with this we are able to see how the radial PML is functioning, and we will also see now what is the role of the radius of curvature. As I told you, as the radius of curvature is going towards infinity, we will be able to go more or less like a plain rectangular PML, but in the case of radial truncation, also on the spherical truncation, it will be not infinity, it will be finite value, so R1 and R2. So what we are interested is what is going to be the impact, what is going to be the ideal or a rule of thumb value for choosing what should be the radius of curvature, and we will see how this is going to impact with this example as shown here. So this is the example where we are able to compute the scattering parameter, the S11 of example, and we are able to see that as the frequency is increasing, we are able to see that. So this is an example of waveguide truncation where I have kept the measurement points as I have mentioned in the previous case, and I am truncating with different radius of curvature. So the Syllo-Mueller boundary condition is behaving as expected, worse than the other possible cases of radial truncation, radial UPML. As you can see, for any case the radial PML is better than the Syllo-Mueller boundary condition. The question is, can we go closer and closer to theoretical value? Yes, we can. As we increase the radius of curvature bigger and bigger, we see that our PML performance is becoming better and better. You might ask, what are these ripples? These ripples are coming because of the reflected field, and they are pretty much in a periodic manner. As you can see, as the radius of curvature is changing, the ripple position is also going to change, or the kind of the effect that is coming from resonance is also going to change. When I have RC, the radius of curvature is equal to 100, you can see that the resonance is somewhere in the 20-21 gigahertz region, and I am increasing it to R equal to 1000, and you see that it is moving away, and R equal to infinity is pretty much the planar truncation, and you can see that the resonance is also, or the kind of the dips what you can see is also moving away. So this shows that the PML is functioning as expected, and it also shows us that we are able to make a good informed decision on what should be our radius of curvature. If we are saying that what we are happy is minus 40 dB and we are interested in, let's say, 20 gigahertz application, you can pretty much go with that with RC equal to 15 mm, as you can see here. But if you are saying that we want to have measurements accuracy of minus 60 dB, and then you have to probably go for RC equal to 100, and you are interested in frequencies, let's say 10, 11 or 12 gigahertz. So this is a way in which you can understand the performance of the PML and the numerical accuracy or the numerical error that you can expect from the PML and make an informed decision based on that. So with this we will stop here, and in the next slides we will discuss about examples related to horn antenna and also other more advanced antennas. Thank you.